All right. So let's start momentum by just, what do you know about momentum? What does that word mean? Mass times velocity. So what does it mean? What does it represent? When you do mass times velocity, what does that give you? Sure, Mike.
I just had it. Like I mean, the unit is joules. It's like
Okay. I feel like you guys are maybe trying to be too technical here. I'm looking for more colloquial, day-to-day. You know, I think momentum's used pretty commonly, right? Like the Juggernaut from the X-Men, right? Has infinite momentum. What does that mean, though? To have infinite momentum? Yeah.
Well, colloquially, when something is moving, it's hard to make it stop.
Okay, so it has a lot of momentum. It's hard to make it stop. It's hard to change its speed, hard to change its direction. It's hard to accelerate, right? It has a lot of momentum, for sure.
So like if something's moving fast and it's really heavy, I guess it's not the technical way to say it, but you say it has a lot of oomph to it.
Yeah, perfect. A lot of oomph to it. When we're trying to visualize and kind of give meaning and kind of visualization to oomph, it's forceful, it's impactful. There's a lot of maybe you can say there's a lot of energy behind it, but we'll refine that definition a little more. But when we're talking about momentum, something that doesn't have a lot of momentum, we would say probably is easy to stop, right? Easy to move away, right? And something with a lot of momentum, not so much. So, for example, you can have like a fly or like a BB from a BB gun shot, and it goes pretty fast. It can go pretty fast, but it hits your windshield and nothing really happens. Not much momentum in it. Whereas if you have a train doesn't have to be moving very fast. A train can be moving just 2 miles an hour, 3 miles an hour. But if you try and stand in front of the train, it's going to be very hard for you to try and stop. Well, the train has a lot of momentum, even though it's not moving very fast, right? So oomph is not necessarily just how fast it's going. It's more about how easy it is to change how fast it's going, right? Fly or bug going down, you're going 60 miles an hour, it's right there, and boom, it's gone, right? Okay, so that is, we will go through technical definitions of momentum, but I want you to kind of maintain that kind of impression or gut meaning of momentum is how easy it is to change its speed. There's another term that we've really honestly used already to kind of describe this property of an object where it's hard to accelerate. What is that? Inertia. It's mass, right? It's mass. So your momentum is really tied to the mass of an object, and all we're doing is we're kind of combining into that fact that if you have something massive and it's moving really fast, there's this property there where it's more oomphy, right? The faster it's going, it has more oomph. In addition to the fact that it has a lot of mass. And so that's why when we say it's mass times velocity, it's really a combination of those. But let's look where the mass times velocity really comes from. Why it's mass times velocity. So I'm going to put 2 equations up here. And I'll put them side by side. 2 equations you already know. One is Newton's second law. Now, for this example, we're just going to imagine one force, nothing else. Okay, so like a satellite just floating in space, in deep space, really far from any planets or any kind of gravitational effects, and it starts, firing its thrusters, and it's just being pushed along, right? So, in addition to this, we know that from kinematics, if you have a constant acceleration on an object, its velocity will change in a particular kind of way. And we take this graph and we take this equation and we graph it out. We graph our acceleration versus time. And if you have constant acceleration, oops. Okay. If you have constant acceleration, then your graph kind of looks like this. It's flat, right? It's constant. And then we said that, well, the velocity versus time graph for this, because it has a constant acceleration, the acceleration is kind of like the slope, right? It's kind of like the slope. You might have some initial velocity, doesn't matter, but your acceleration is like the slope. And so if I took this equation and I rearranged it to say v minus v naught equals to at, or really saying this is like a change in velocity, then we found that this, roughly speaking, kind of looks like an area of a rectangle. It's like a base times a height, so that if you travel for a certain amount of time, right, if you go for a certain amount of time t, there's a certain amount of height a, right, and that area, if it's just base times height, turns out it's the same as your change in velocity. Right? So that should make sense. You take your acceleration, you apply it for a certain amount of distance, and then you lead to a certain height change, and that is your delta v. Right? So if you go for a certain amount of time, a certain slope, right? Pretty straightforward. So here's acceleration, here's time, it's related to velocity, here's force related to acceleration. So if I were to turn this delta v equals at into like a force, what I could do is I could multiply both sides by mass. And so that kind of turns my right-hand side into a force times time. Right? Okay. So one thing that is going to start coming up and is important to investigate with these units, we're going to have to incorporate a little more calculus than we have in the past. Okay, so far, we've talked about what derivatives are. Okay, we said a derivative is kind of like an instantaneous rate of change, so that this acceleration would be the derivative of the velocity, right? Which is this kind of the same thing as if you had a average acceleration equaling to a net change in velocity over some total amount of time. As you look at a more instantaneous moment, that's what the derivative is. Okay, the derivative is just the slope at a particular moment. That's all this derivative means. So then if this represents the slope, there's also a meaning behind this area, or a way of mathematically representing this for not a net change, but kind of almost an instantaneous amount. And that is the integral and when we say the integral of this, okay, the integral of the area, or sorry, the acceleration graph, essentially what that means is you're taking, instead of instantaneous slopes, you're looking at instantaneous areas, and then you're just adding them all up. You're taking a bunch of little rectangles of like infinitesimally small space, dt. Okay, dt in an integral, the meaning behind it is that that is the slice that you're taking. You're taking small slices of time, and you're multiplying it by the acceleration at that time, and then you're adding all those areas up. And if you add all those areas up, that gives you the change in velocity. That's what the integral really means. This is useful because in this case, we're taking the areas of little rectangles which are inside of another rectangle. But if this function started becoming more complicated, then you have a bunch of little rectangles of different size. And when you add those up, that still gives you the change in velocity. And that becomes very useful because obviously not all objects accelerate at a constant rate. Okay, so that means that if I can take this constant acceleration kind of equation and turn it into a relationship between my kind of a mass times velocity minus a mass times initial velocity. This is kind of like a change, right? When we talk about change in velocities, is equal to this ft. Okay. Then I should also be able to represent that with an integral as well, right? If I can represent this one with an integral, then I should be able to represent this one with an integral. So what would that integral look like? What do you think? How would I if this transforms into that, if this is saying the same thing as this, how do I say this with an integral? I'll write that. Yeah, Akif.
Integral of force dt.
Integral of force dt. And then I'll write this again. Perfect. Okay. That's it. Okay. All we did was, previously when we did kinematics, we just had accelerations. We just somehow magically knew what they were. All we're doing now is we're saying that in order to have those accelerations, you must apply forces. And forces have to take into account the mass. That's the only difference. So a mass times a change in acceleration is a force, which leads to a mass times a velocity, which is a momentum. So this is your momentum. Okay. Notice that momentum is kind of a property at a moment for an object. So an object has a certain mass and a certain velocity, so it has a certain momentum. It's also worth noting that momentum is relative because it's based on velocity, right? So if you have two cars driving down the freeway and they're both going 60 miles an hour and they're side by side, if you're in this car's reference frame, the other car looks like it has no momentum because it looks like it's not moving. They both have relatively zero velocity relative to each other. Okay, so momentum is a relative thing. It's at least as far as classical mechanics go. Okay, so everything that we talk about in this class up until you start getting to general relativity and things go really, really fast, or as long as things are not really, really fast towards the speed of light, and as long as they're not really, really small, like the size of protons and neutrons, then all of this stuff works out pretty good. Okay, so momentum then at that point within this range is relative. You can have zero momentum even though you might be moving, relative to something else. All right. On the left-hand side, this is what we call impulse. So just from the look of it, how would you describe the difference between impulse and momentum? They kind of look like they're describing the same thing, but they're not. Yeah.
Impulse is the change in momentum.
Yeah, it really is. It's the change, right? So impulse is when you apply a force on an object for a certain amount of time. Everything that we've done in chapter 5, 6, 7, 8, and 12, we never mentioned time, ever. We never looked at how long we applied those forces. We just had you have this elevator, it's going up, and things are accelerating, there are normal forces and whatever. Or you have a car on a bank turn, and there's friction, but as far as the problem was concerned, it's like in that state forever and ever and ever. You're never concerned with how long it happened for. But that doesn't help us answer a question of, say, you have a baseball hitting a baseball bat hitting a baseball. It only happens for a short amount of time, and the force on the baseball is not constant. It ramps up because it's the compression of the baseball and then the elasticity of the baseball as it kind of expands back out that, you know, the forces are changing. It only happens for a split second. So it is not very convenient to use the kind of math that we've done you've been using for a scenario like that, because you don't want to try and do kinematics on a baseball where at a moment it's accelerating a lot and then it's not accelerating anymore and you have everything in between. It's too complicated. So some notation things. On the left hand side here, the impulse, we use the symbol J, capital J, to represent impulse. Okay. And on the right hand side, we use P to represent momentum. Okay. P, lowercase p for momentum. When we get to energy, uppercase P is used for power, which is something else. Okay. So momentum has a very specific mathematical meaning. Impulse has a very specific mathematical meaning. Your impulse is how long your force is pushing on something, and that will result in a change in momentum. Okay? Questions on terminology, meaning, any of that? So let's take a look at the graph of momentum. What kind of graph do we want? The function we're interested in is the force over time. And so, again, if we have a constant acceleration, we must have some sort of constant force. So we have a force versus time graph. And we have a constant force. Then the area under this graph is your change in momentum. Okay, let's go ahead and kind of write that out. So the impulse equals the change in momentum. Important definition there. If you ever get into, for example, rocketry, there's a thing called specific impulse. Specific impulse is kind of a way of measuring, again, a kind of a net change in velocity, depending on how much fuel you have and what planet you're on, what the gravity is, and so on and so forth. So this idea of impulse is like a measure of net change in motion. Taking a look at the units, you'll see that if you have kilograms times velocity, so kilograms times meters per second, so you can either have kilograms times meters per second, or sometimes it'll be a Newton second. A Newton second tends to be pretty common. And if you're not sure about why it's also a Newton second, well, a Newton is a kilogram meter per square second. So if you multiply the square second with the second, that gives you kilogram meter per second. So they're the same thing. They're the same thing. All right. Any questions so far? It's worth mentioning that this was kind of taking the integral approach. So if your momentum is kind of the area under this force versus time graph, right? Then there should be kind of a corresponding slope kind of a graph, right? The slope of something should give me my force if the area under my force gives me my momentum. And so it's actually kind of interesting to take a look. We said that a force is equal to a mass times acceleration, but an acceleration is a is a rate of change of velocity, right? So actually, if you want to know an instantaneous force, it's actually, this F equals ma really comes more from, a better definition of this is actually the rate of change of mv. This is actually a better definition. So F equals ma is actually not really the original equation. It's actually originally this. And so, or you can say dp dt. In other words, when Isaac Newton was figuring all of this out, he had the idea of momentum in mind more so than just change in velocity. In other words, it was this, you had, in order to change the oomph of an object, you had to push or pull on it, right? That was what kind of more the meaning of Newton's second law. Okay, so then that means that if you were to graph a momentum versus time graph, and you had some sort of changing momentum, then the slope of this would be the force. Right? So that's how it goes both ways. Your area under your force versus time graph is your change in momentum, and then your momentum versus time graph, its slope is the force. Okay, one last thing to mention about momentum and force and impulse and all this is that a force is a vector, right? So is velocity, so is acceleration. All these are actually supposed to be vectors, which means that if you go back to this one, the most general form of this, all of those should be vectors. Your impulse is a vector, your force is a vector, which means your velocities are vectors, which means changing your velocities is changing velocities based on the vectors, and then your momentum, all of it. All of it is vectors. Okay. So what that means is the same way we treat all other vectors so far, from kinematics to forces, you want to break it down into its x components, y components, you break it down into its components. So all of this behavior here, when I write it without any vectors on it, is you can think of it as looking in one particular direction. If this was the force in the x, it will cause a change of momentum in the x over a certain amount of time. And then you can take the force in the y, will result in the change of momentum in the y, so on and so forth. Okay, which means, again, all of these vectors, vectors, vectors. Mass is not a vector, it is the velocity that's the vector, which makes momentum a vector, and so on and so forth. Okay, those are all, the direction matters. The direction matters. Okay, so let's take a look at how direction matters. Let's say, for example, you have a person. Let's just say, for instance, for example, you have a person and he's kicking a soccer ball. Okay, a soccer ball is coming down and then he kicks it and it goes back up. Okay, and if we look at let's say the mass of the soccer ball is half a kilogram. Kind of a heavy ball. It's like a pound. I don't know if that's super heavy or not. Anyway, let's say it's going downward at 5 meters per second. Sorry, I kind of don't have much space here, so I'm going to zoom in a little bit. And then it gets kicked up, and now it's going upward at 5 meters per second. Okay, so how do we calculate the impulse on the ball? Okay, the impulse meaning the change in momentum. Let's look at the initial motion and then the final motion. So initially, it's going downward. And so again, since we're dealing with vectors, right, we have to choose our coordinate system. Let's say upward is positive. So then the momentum initially will be 0.5 kilograms times a negative 5 meters per second. And so this will be a negative 2.5 Newton seconds of momentum. Okay. Afterwards, it gets kicked. Sorry, there shouldn't be anything here. The momentum afterwards is 0.5 kilograms, 5 meters per second up, which is 2.5 Newton seconds. So it was initially 2.5 Newton seconds down. Now it's 2.5 Newton seconds up. What is the impulse? Five. In which direction? Positive. Up. Yeah. So you can do it really kind of, in this case, pretty intuitively. It was going down, now it's going up. So it must have been pushed up, right? The impulse, being the change in momentum, is the final minus initial. So that's your 2.5 Newton seconds minus your negative 2.5 Newton seconds. And so it equals 5. Okay. Depending on the question, if it asks for the magnitude, you can just put 5. But if it asks for magnitude and direction, you should mention that is up. All right. So what makes this so useful is we can kind of determine a lot of different things that are going on here with the motion of the ball and the forces involved with the ball. You know, if you were to graph the force versus time graph on this, start zooming out a little bit. If you looked at the force versus time graph for this, it wouldn't necessarily have to be at, you know, straight lines and so on and so forth, right? That's not how it behaves in real life. It might just go smooth like that. Right? You have initial contact, and then the ball starts to compress. You get the maximum amount of force that's starting to accelerate it upward, and then the ball starts to leave and it starts expanding and then it loses contact, right? So it's going to be smooth realistically, and we said that this area is the change in momentum. Right? There's a couple kind of neat things that we can do with this. If we can time how long the contact of the ball is with the foot, we could calculate like an average force. Okay, we can calculate an average force. So one thing that can come up, and calc people, you'll probably, hopefully you'll see this. I think it is the fundamental rule of calculus or something like that, which is that if you take the integral of this force dt, right, it will equal to the average force times whatever time that you're looking for. So you can kind of find like an average force that is kind of representative of the mean slope, whatever, on your momentum change. Anyway, sometimes you may want to know that. Sometimes you'll want to know what the average force is, and so your average force is equal to your average force over some time equals to your change in momentum, and that can be useful to know. Okay. Any questions on, this is kind of a lot of stuff, but frankly, chapter 9 is only like 16 or 17 pages. We're doing this for 2 more class periods. Going to do a collision lab next week before your 4-day weekend. And this is really the main parts. Okay, this is essentially what you use momentum for. Questions? Okay, so I'm actually going to scan these notes, but if you've been copying it down, it's good for you. Keep doing it. Don't just be like. Okay, so Sadia asked for story time. I'll tell you a story about this. I'll leave the notes up. Okay, I'll tell you a story about the importance of taking notes. When I was an undergrad, my senior year, I was getting pretty good grades, and I was feeling pretty cocky about myself, so I decided to take a graduate level class while I was an undergrad. And I took this class called Kinetic Theory of Gases. And the professor was pretty great. I loved the guy. He was actually, I think, the chair of the aerospace department. And his class was like at 7:30 or 8 in the morning or something like that on the other side of campus. And what ruined me was he recorded every class. He recorded every class. So what happened was, I went to the first couple weeks, and then it was early in the morning, and I didn't go. And I would just be like, well, I'll just watch the classes, And after like 2 weeks of saving up all these classes, I knew on the calendar there was a test coming up. And so the night before, I watched all the classes, right? And I get to like the 3rd or 4th one, and he says, we're moving the test up. It was yesterday. So I totally missed the test, and then I had to drop the class because I missed the test entirely. So I ended up, I dropped it, but it didn't matter. Like, it didn't count because it was early enough in the semester. And then I ended up taking it when I actually went to grad school. I got an A, and it was fine. It was a good class. It was an interesting class. It was just,